In today's lecture, we're going to talk about two systems that we haven't talked about before, though at least one of them you've talked about in 358. So the first will be paramagnets. A paramagnet is a set of spins where the spin is associated to a magnetic moment and the spin wants to align to ambient magnetic fields, but depending on the temperature, they either will or won't be able to align strongly to the ambient magnetic field. And the second system is going to be molecules, specifically diatomic molecules, and looking at their rotational excitations. These are both interesting systems in terms of they come up a lot in the world and they're relatively easy to calculate, though we're going to learn a few calculational techniques that come up pretty regularly in statistical mechanics by looking at these particular systems. Today's lecture will be relatively short because Wednesday's lecture will be relatively long. Just happens to be that conceptually the material for this week sort of breaks up into two nice packages this way. So first, the paramagnet. So in a paramagnet, you're thinking of your atoms as having a spin associated to them, and that spin gives rise to a magnetic moment. Here we're looking specifically at a two-level paramagnet. So either spin up or spin down. That means we've got spin 1/2 particles. So if you had a single unpaired electron in your atom, it's probably going to look like a spin 1/2 paramagnet. In fact, most elements and a lot of compounds have this paramagnetic behavior, though maybe not exactly like a spin 1/2, but spin 1/2 is the easiest case. So what we're looking at is, we've got spin up and spin down. The energy, and actually let me be a little careful. I don't want to say spin up, spin down. What I want to say is magnetic moment up and magnetic moment down. Okay, so for an electron, the magnetic moment and the spin actually point opposite directions. So let's just keep this sort of physically neat and say magnetic moment up or down. Magnetic moment's a long thing to say. Let's say dipole up, dipole down. That's going to be easy, right? So the magnetic dipole either points upward or downward, and the energy is minus the dipole moment dotted with the magnetic field, right? So the minus sign means if my magnetic field points upward and my magnetic dipole aligns with the magnetic field, that's the lowest energy configuration. And now if I try to rotate the magnetic dipole to oppose the field, I have to do work on it, right? Its energy is going to go up as I do this. Okay, and I keep saying up or down because I'm assuming here that the magnetic field is oriented in the z direction, positive z direction. Okay, so just to put together what I said and what the equations tell you, the energy of a dipole up minus mu b, where mu is now going to be sort of the magnitude of the magnetic dipole, and the energy of dipole down is positive mu b. One reason you do the spin 1/2 paramagnet is you can write down the partition function quite easily. It's only got two terms, right? So z is e to the minus beta e up plus e to the minus beta e down. And we just said what these are. E up is negative, so negative, negative, we've got beta mu b. I've tried to be careful to make the betas and the b's differentiated. So we've got e to the beta mu b plus e to the minus beta mu b. And that sum is twice the hyperbolic cosine of beta mu b, or cosh of beta mu b. Now, if you don't have experience with hyperbolic functions, I would encourage you to pause the video and just take a few minutes looking them up. I think the Wikipedia page on hyperbolic functions is pretty good. There's nothing about, alien conspiracies to murder JFK on that page. It's all pretty solid math. So just check it out for a few minutes, get the main idea of using these hyperbolic functions, but I think you should have seen them already. Just take a moment if you haven't. Okay, Now we're going to use the partition function we just calculated and learn something physical from it. So the first thing to look at is the average energy that a dipole will have in a certain field at a certain temperature. So again, from last lecture, we know that the average energy, or the expectation value of the energy, is minus 1 over z dz d beta. And there's a slightly easier way to remember, which is minus dd beta of log z, but in this case, to do the actual calculation, taking the log of cosh is not going to be terribly helpful. So, okay, minus 1 over z dz d beta. This 1 over z is here, and if you either remember or you just took your time on Wikipedia, you'll know that the derivative of cosh is sinh, the hyperbolic sign, and of course, chain rule is going to kick out a mu b. So we've got 2's that cancel, and sinh over cosh is tanh, hyperbolic tangent, and it all comes together like so. So one nice thing about the spin half paramagnet is not only is it easy to write down the partition function, but now because we have it in terms of elementary functions, all of these sort of turn the crank things where you can use the partition function to calculate physical quantities go pretty straightforwardly. So there we've got it. The average energy turns out to be slightly negative because we know beta mu b, this is going to be positive because beta is always positive, and mu and b are both magnitudes that are also always positive, and tanh of a positive is a positive. So we've got some negative average energy, and the other thing that we can say is if we've calculated for a single dipole. If we're looking at the average energy for a set of n dipoles, maybe a large set, maybe we're looking at some chunk of matter and we want to know what's the average energy of this chunk, not just the average energy of a single dipole in it. These dipoles don't have any correlations between them. They're just independent little dipoles, and so you can just stick an n out front. It's just n times the average energy of a single dipole. Now, let's look at the next interesting quantity, which would be the average of the dipole. Okay, so what I mean by that is, on average, are more of these dipoles pointing up or pointing down? And what fraction of them will be pointing up versus down? And when we take the average of the dipole, that means something like the up dipoles minus the down dipoles. So that's what I've written here. It's the magnitude of the dipole times the probability that it's up minus the probability that it's down, right? So, and I should point out I put mu sub z here because we're looking specifically at the component that points along the magnetic field, right? So magnitude of the dipole times the probability that it's up, because then its value is just mu, minus the probability that it's down, because if it's down, then its value is minus mu, right? So difference of the probabilities, and that gives us mu over z times the difference of the Boltzmann factors, right? All I've done is factor this 1 over z out. It'd be Boltzmann over z gives you the probability, pull the z out. And now we've got the difference of these Boltzmann factors. Before, when we were calculating the partition function, we had the sum of these factors. Their difference just gives you the hyperbolic sign instead of hyperbolic cosine. So we've got 2 sinh beta mu b here, and put it together, we get a mu tanh beta mu b. Okay. Now, if you're looking at this and you're saying, mu and a tanh, this sounds familiar. It should sound familiar. Because there's sort of, I'm going to say an easier way to do this. And what I mean by easier is not necessarily in this particular calculation it's easier. It's a conceptual approach that in a lot of problems could save you time. For instance, if I had given you the spin 5 paramagnet, so now there are 11 sublevels instead of 2. This next approach would be substantially quicker. And that is to observe the average energy is, well, energy is minus mu b, so the average energy is the average of minus mu b. But b is just a fixed thing, right? We've got this z direction magnetic field, its magnitude is b, that's not changing. So really the only averaging is over the dipole, okay? And since b points in the z direction, it's going to be the average of mu sub z. Well, this is what we wanted. Average energy is what we already had, okay? And we have this great formula to get that from the partition function. So just solve for average of mu z, right? It's going to be the expectation value of the energy on top. We'll divide by minus b, right? Minus b. That's in the bottom. And then we get exactly what we got up here. Okay? So this idea that the average energy is relatively easy to calculate, right? If you've already got the partition function, you have a formula to go from that to the average energy. Whereas for this average of the dipole direction, we don't have sort of a magic formula for that, right? You would have to go through with the probabilities as we did up here. But, you know, if this is sort of an infinite state system or a system with, like I said, 11 states, that might be cumbersome. So anytime you want to know an average quantity, the first thing to check is, does it have a simple relationship to the average energy? Because if it does, you can leverage the way we can calculate average energy to calculate your quantity of interest. Okay. Now, if we had a chunk of stuff, like we said before, this average of the dipole direction can be used to get the magnetization. Okay, and so the magnetization, again, the dipoles are independent. So the average of the dipole direction for one dipole is the average of the dipole direction for the next, and so forth. So the magnetization is just n, your number of dipoles, times the average of the dipole. And that is just n times our average, which is to say now we have our magnetization of the material. Now, again, it's nice to have a closed form because we can look at various limits. Two physically interesting limits here. One is high temperature. And let me just, because this lecture is going to be a little short, let me just be a bit expansive here. Whenever we say high temperature, or really if we say high anything in physics, your immediate question should be high compared to what? Okay. If I tell you this is a high mass object, high compared to what? Right? Is it heavy compared to my cup? You know, does it have a big mass compared to the Earth, compared to the sun? What are we comparing to? Because really, you can only say something is big or small if it's a dimensionless quantity, right? If something's much smaller than 1, then you know you can do a Taylor series and you can quantify the size of the first term you ignored, because, you know, you can say, oh, well, I went to second order and my parameter is 0.01. So 0.01 squared is 1 over 10,000. That's very small. I must have made a good approximation. But what's a kilogram squared? Well, I don't know. Is that big, small? It depends on what's out front, and what's out front is going to have units. So whenever you want to make an approximation by saying this thing is large or this thing is small, you need to tell me what are you comparing it to, right? So if I'm expanding in small mass, say, for something that's a kilogram, because it's part of a larger system that's 10,000 kilograms, right? Then I've got an expansion in 1 kilogram over 10,000 kilograms. Now I know my expansion parameter is small because it's 10 to the minus 4. Okay, so when we say high temperature, what are we comparing the temperature to? Well, there's only one sort of relevant energy scale in the problem of the paramagnet, and that's mu b, right? The energy available in an interaction between a dipole and a magnet and the magnetic field. So when I say high T, what I mean is the energy kT is much bigger than the energy mu b. And the payoff of that is that when I take beta times mu b, right? That's mu b over kt. This will be very small. So now I've got a small dimensionless parameter. Now it makes sense to say high T. So what do I mean by high T? I mean beta mu b goes to 0. So when we look at our formula for the magnetization, that's the argument of tanh. So if we take the argument of tanh to 0, we can just look at the first term of the Taylor series for tanh, which turns out to be just x. Tanh has a nice Taylor series, at least to start with. So this guy is just going to pull out. Our magnetization is n mu squared beta b. It's got 1 power of beta, which means 1 power of 1 over T. So the magnetization is proportional to 1 over the temperature. Okay. Or said differently, as the temperature goes up, the magnetization goes down, and that's Curie's law. Okay. The other physical thing to say here, you could kind of guess this formula, really, at the end of the day, by just saying, well, look, it should be proportional to the number of dipoles, right? If I have twice as many dipoles, I'll have twice the magnetization, as long as they're all identical and independent. I polarize the sample with my magnetic field, so it ought to be proportional to the magnetic field. And why would it look like mu squared? Well, mu tells me how strongly I interact with the magnetic field. So if I have a stronger mu, I'm more likely to align my dipole to the field. Also, mu tells me the strength of my dipole. In other words, mu both controls how well I track the magnetic field and how much field I'm producing by tracking it. So we get a mu squared. So this sort of, in retrospect, this formula makes sense. And that's another thing that I'll maybe be just slightly expansive on. When you're doing your problem sets, you should be checking your answers in this way. In fact, it's good to think before you start the problem. Can I guess anything about the answer, right? If you can guess certain properties of the answer, then do the calculation. Check that your calculation matches that guess. If it doesn't, there's a pretty good chance that you went astray somewhere, and you can go back and check your calculation. So if we had done this analysis first and said, gee, how do we expect the magnetization to look when the temperature's high? I'd say something like, well, at high temperature, the difference between spin up and spin down is going to depend on mu beta over kt, and that's going to be small, but our polarization is going to depend on that. And then once we're polarized, however much polarization we have, and mu times that will give us the magnetization from that polarization. So, like I said, if you think about the physics beforehand, you can almost guess the answer. Now, there might be a prefactor. It turns out in this case there isn't. There's no like 1 over square root of 2 pi or something to catch you. But okay, so thinking about physical limits, you can do before the problem to help you know you've gotten the right answer at the end. But also, of course, we do the calculations so that we can learn about these physical limits. The other physical limit is low temperature. So beta mu b now is going to go to infinity, right? Because if mu b over kt and the t gets small, the denominator is small, this thing's going to blow up. So beta mu b goes to infinity. Well, what happens up here? Tanh is an interesting function. As its argument goes to infinity, tanh becomes 1. Okay. So if you think it's sinh over cosh, each of these has an e to the x and an e to the minus x. And as x goes to infinity, the e to the minus x term does not matter at all. So this just becomes e to the x over 2. This becomes e to the x over 2, so tanh is just 1. It's the ratio of 2 enormous, essentially identical numbers. Cool. So in the low temperature limit, this dependence goes away, and you're just left with n mu. Okay. Again, physically, this should make sense, right? If the temperature's low, what that means is the interaction with the magnetic field, that energy mu b, is much bigger than the thermal energy kt. So you're not going to have enough energy to excite your dipole to point in the wrong direction. all the dipoles will be dominantly aligned by the magnetic field. And yeah, there's maybe, we could do this to the next term, and there's some small jittering, but essentially you're going to line up with the field. Our second system is rotation of diatomic molecules. So a diatomic molecule, it's two atoms bound together. This is a sort of dumbbell-looking molecule that you've seen in chemistry, no doubt. Diatomic molecules are important. It's what we breathe, for example. So oxygen's a diatomic molecule. Most of our atmosphere is diatomic molecules, either nitrogen, N2, or oxygen, O2. So those are important. Let's look at them also because they turn out to be a system that is relatively straightforward to calculate, and the technique we use is important in the future. So in a diatomic molecule, okay, we're looking at a quantum mechanical system. So if you think back to what you learned about angular momentum in quantum mechanics, right, we're going to look at a rotating molecule. So you have different m sublevels for every j level. And this is just like in the hydrogen atom, you have different m sub l's for your capital L levels, right? The S shell just has a single m equals 0. The P shell, because L equals 1, it has ml equals -1, 0, and 1. Same story here. When J, the angular momentum of the rotating molecule, is 1, then you've got -1, 0, and +1. You've got J equals 2, -2, -1, and so forth, minus J equals 3. The other thing that you'll notice here is that the energy spacing gets bigger as you go to higher J. So the formula for these energies is epsilon, which is just a constant. It's called the rotational constant, and that tells you sort of the energy scale for rotations. The dependence on J is J times J plus 1. Okay. So again, this should sound familiar from quantum mechanics of the hydrogen atom, right? You've got L squared, gives you the energy due to angular momentum. And when that L squared operator acts, it gives you a value of L times L plus 1. Okay, so same story here. Our number of states is 2J plus 1. Just check that real quickly if you want. And our energy is epsilon J times J plus 1. So we can take that information, we can immediately write down the partition function, right? Because the partition function is the sum of the Boltzmann factors. Here's our Boltzmann factors. Weighted by the degeneracy. Here's our degeneracy. So this is technically the partition function. We're done. Okay. Except it's not a very convenient form to work with. We'd like to see if we can boil this down to something easier to work with. And the way we're going to do that, I'm going to take this whole thing here and just call it f of j. Now I can plot f of j along a j-axis. This, of course, is completely unforgivable that I've not labeled the axis as j-axis, but I'm telling you now. So I can plot it along the j-axis like it's a real function, except it's not. Sorry, I shouldn't say a real function. Plot it like it's a function of a continuous variable, which it is not. Okay. But if we just put little bars, right, that shows you that it's a function of a discrete variable. But of course, I have already kind of tipped my hand a little bit here because I've drawn a smooth curve through the centers of these bars. Okay. So what we want to do is say, I need to calculate the sum of f of j. I'm not so good at sums. Integrals are more to my liking. Does this look enough like the smooth curve that I can do the integral? And if I say this integral, it equals this sum. Essentially, the issue here is how quickly is the function changing shape, right? So something that changes very jaggedly, if you try to draw a smooth curve through it, you're going to be missing a lot of the structure, okay? Or I should say maybe trying to fit a smooth curve through it is going to exaggerate some places and cut off the rate. What we really want is the sum of these rectangles. And you see we're cutting off the corners, but in the function that I've drawn, it doesn't look too bad. So you can check this more carefully, and what you'll find is, in this case, to do this sum as an integral, this is essentially a high temperature expansion. So we're assuming that beta epsilon is small. Remember, high temperature is small beta. So if beta epsilon is small, then this exponential, which is the sort of the part of this that could be changing very rapidly, it's not. Okay, the exponential has a small coefficient in the exponent, and so when we go from j to j plus 1, the function isn't changing wildly in between. Okay. So that's going to be what we need, is a high temperature. Beta epsilon is relatively small. It turns out beta epsilon of 1/10 is already quite good for this. You'll get to look at this a little bit more on the next homework. So we're going to approximate the sum as an integral. Great, let's write it down. So z is approximately, again, the integral from 0 to infinity dx of, we're just going to change the j's to x's, right? 2x plus 1, e to the minus beta epsilon, x times x plus 1. And now, how do I do this integral? Well, there's a pretty straightforward substitution. This is x squared plus x. If you take the derivative, you get 2x plus 1. Hey, there's a 2x plus 1. Great, so we can just do a u substitution here. Our u that we do the substitution for is going to be beta epsilon x times x plus 1. So we need to put a beta epsilon out here, which means a 1 over beta epsilon out front. And this converts into this integral. It's just the integral of an exponential. We could do that. And it's from 0 to infinity. At infinity, this guy goes away, so we're just left with 1 over beta epsilon. So the partition function that looked, maybe a little imposing up here, by turning it into an integral as an approximation, we've got an approximate answer. And again, this is in this sort of beta epsilon is small expansion. Next thing that we want to do, we've got a partition function. Let's calculate an average energy. And this is the average energy in the rotational degrees of freedom of these molecules. So we're saying, next lecture we'll talk about translation, right? So if we've got a gas of oxygen, of O2, these molecules are rotating, that's what we're looking at now. But of course they're also moving around, right? So there should be something more to their total partition function in terms of their translations, their speed, right? That gives them an energy as well. In fact, probably when you were in, grade school and somebody tried to explain temperatures, well, these molecules, they move really fast. We haven't talked about moving molecules too much, but we'll get to that in the next lecture. For now, we're just looking at their rotation. So the average energy of their rotational motion, well, we've got the partition function for their rotational motion, so let's do it. Minus 1 over z, dz d beta. Minus 1 over z is here. dz d beta is another minus sign, 1 over beta squared epsilon. All bunch of things cancel, and we just get 1 over beta. So that's satisfying. We got a very clean, simple looking answer for the average energy in the rotational degrees of freedom. Now, I have put a box around this in almost the same form, just changing beta into kT, right? Changing 1 over beta into kT. So the average energy in the rotational degrees of freedom is kT. I say this, put a box around it in a different color, because this is a point that we will come back to in the next lecture. This is sort of a hint of something called the equipartition theorem, which you potentially saw bits about in 358. We're going to look at it in the statistical light, and it's going to make a lot of sense. Great. So the last thing I want to do just before we wrap up is to talk about, there's something that Schroeder mentions. I felt like maybe he didn't explain it terribly well. I think there's a problem where he explains it better, but just to tell you what's going on here. I keep saying O2, but the calculation that we've done is not quite right for O2. Okay. And the reason for that is O2 is homonuclear, right? So both ends of this dumbbell molecule are oxygens. If you have identical atoms making your diatomic molecule, you have to think about the exchange symmetry of the wave function. Now, hopefully that's something that you've talked about in quantum, but the basic idea is if I have a composite system made out of bosons, right? Then if I exchange two bosons, the wave function should not change sign. Okay. So two oxygen atoms, each oxygen atom is a boson. Okay. You can tell that by counting up all of their fundamental particles, right? It's 8 electrons, 8 protons, 8 neutrons, so oxygen is a boson. That means if I exchange the two oxygen atoms in their wave function, the sign shouldn't change. So my state overall has to be positive parity, that is to say, the sign does not change when I swap my two atoms. Okay? And these oxygen molecules, and actually, let's not do oxygen, let's do hydrogen, because hydrogen is simpler. It also is naturally a diatomic molecule, so when you find hydrogen, you don't find random hydrogen atoms floating around, you find hydrogen molecules. So the hydrogen molecule has a spin in the nucleus, and the spin of the nucleus, it's a spin and a half, so either up or down. If the two spins point the same way, then the spin wave function is symmetric. If we swap the two atoms, well, the spins were the same, so the wave function hasn't changed. It's positive, in other words, the sign doesn't change, when we swap atom 1 and atom 2. Overall, the wave function has to be symmetric. It has to not change sign when we swap the atoms, which means that the spatial part of the wave function has to also be symmetric, right? If I swap the atoms and the spin part doesn't change, overall it doesn't change. That must mean the last bit doesn't change, right? If this changed sign, you'd have a minus and a plus. This would end up minus. So, oh, I put R here. This is a bad molecular physicist moment here. So when you're talking about real molecules carefully, they have a lot of different types of angular momentum. We're ignoring all of that and just looking at the rotational part. The rotational part is actually called R usually, but let's fix this. We've been referring to this as J. Let's not be confusing in the notes. This is J. Okay. So it turns out the rotational wave function, or the spatial wave function, is symmetric if the rotational angular momentum of the molecule is 0, 2, 4, okay, only even values of J. Similarly, if the spins are in opposite directions, the spin wave function is antisymmetric. So when I swap atoms, the spin wave function changes sign. That means the spatial wave function had better change sign as well, which means only the odd values of J are here. Okay. So if this is all seeming a bit funny, don't worry about it too much. The punchline is really, depending on the spins of the two atoms, you either have the even J's or the odd J's. And I'm even oversimplifying a bit because there are other symmetries that go on. But for hydrogen, let's say this is good. The point being that the number of states that you're summing over to make the partition function is half, right? So in other words, half of these bars just don't exist. And roughly speaking, you can deal with that by putting a half for the degeneracy out front when you do this integral. So Schroeder spends a lot of time on this. I don't really want to belabor it so much, but I did want to try to give you a bit more complete of an explanation of what he's talking about if you're reading the book. And before I close, I should say this is all more or less in the book. This is all from section 6.2 in the book. So if you're following along in the book, we're finishing section 6.2 in this lecture. And like I said, next lecture will be a little bit longer. We're going to cover a bit more, but it gets into doing the same kinds of things, but now with continuous variables like position and momentum. So I'll see you Wednesday.